Modern automated factory floors generate an immense volume of data. Every second, robotics and sensors fire off thousands of data points about their operational health. But despite this massive data generation, legacy industrial control systems are structurally not designed to process it. Their architecture is built for execution, not analytics. The industry standard for these systems is defined by the IEC 61131-3 specification, relying heavily on languages like the ladder diagram. Ladder logic is incredibly effective at what it does. It is perfectly optimized for reliable, deterministic, real-time machine control. When a switch is flipped, the machine responds instantly. The structural divide appears when we ask that same system to perform complex IT-level tasks. Writing a ladder diagram to compile, format, and export predictive maintenance data logs is highly inefficient. This diagram shows a visual representation of the architectural divide between operational technology on the left and information technology on the right. There has historically been a strict wall between controlling the hardware and processing the data it creates. To close this gap, engineers are turning to hybrid architectures, specifically platforms like the Phoenix Contact PLCnext system. The core concept of this hybrid system is the ability to run high-level languages like C++ natively, right alongside traditional ladder diagrams on the exact same hardware. Today, we are going to deconstruct the exact codebase required to link a basic ladder logic motor control program directly into a C++ data logging script. Integrating edge computing capability directly onto PLC hardware without disrupting critical machine control changes how we bridge the gap between machine execution and data analysis. We start our setup at the physical hardware level, using a standard start and stop switch. These physical push buttons are normally open switches, hardwired directly into the digital input module. In the software, we map the physical IN-01 terminal to a start variable and the IN-02 terminal to a stop variable. On the other side of our execution logic, the physical motor maps to output out-01. The primary ladder logic follows a direct sequence. Pressing the start switch instantly activates the motor output. Once running, the motor remains running indefinitely. It holds that continuous state until the stop switch is pressed and the circuit opens. While this ladder logic handles physical execution flawlessly, it is isolated. It cannot independently track, count, or log these activation events for long-term analysis. To build that analytical capability, we shift away from the PLC programming software and into the Eclipse integrated development environment. Inside our C++ project, we will first examine the header file, motor start stop program.hpp. The architectural challenge is safety. The C++ program must extract operational data from the ladder diagram without causing execution collisions or delaying the machine logic. The solution is a mechanism called input and output ports. This creates safe memory mapping between the two distinct runtime environments. Looking closely at the memory port channel, we construct our first specific port, a Boolean input port, simply named motor. This input port functions as a one-way receiver. It reads the physical on-off state data in from the ladder diagram environment. Below that, we define our second specific port, an integer variable named output motor starts. This is an output port. Its job is to capture our activation count and write that integer data out to the wider system. Finally, we introduce a third variable to the header file, xprevMotor. Notice that xprevMotor does not use a port. It's an internal Boolean variable, strictly isolated within the C++ environment to track the motor's state history. By clearly defining these ports in the header file, engineers create a secure data bridge. This isolates complex analytics variables from critical operational machine cycles. With the bridge established, we transition to the execution script, the motor start stop program.cpp source file. The analytical requirement for this script is highly specific. It must count the exact moment the motor starts, ignoring how long it actually runs. Capturing that single fraction of a second requires what programmers call state change, or edge detection logic. This diagram highlights line 10 of our source code, where the core logic occurs. We have an if statement comparing xprevMotor against the current motor state. Let's break down the syntax. The exclamation mark represents a logical NOT operator, and the double ampersand acts as a logical AND. The state condition evaluates a precise scenario. It checks if the previous state was off, meaning false, and if the current state is on, meaning true. This exact false to true transition is the only moment the code will execute. Any other combination is ignored. When that condition is met, the execution flow moves to line 13, forcing the output motor start's integer value to increment by a count of exactly 1. Immediately after incrementing, the script hits line 14, which fires a call to generate the actual log data. To reset the system, we have to look down at line 18. Line 18 overwrites the xprev motor variable with the current motor state. This effectively arms the system, prepping the logic for the next possible machine scan. By utilizing basic logical operators, engineers distill complex edge detection requirements into extremely lightweight, low-overhead C++ execution. And now we reach the deployment phase. Both the ladder diagram and the C++ program are compiled and downloaded together to the physical PLCnext hardware. Once running, we have two parallel operations. On the hardware side, the physical start and stop switches trigger the deterministic ladder diagram to control the motor instantly. Parallel to that hardware control, the C++ code operates silently, continuously monitoring the port bridge for state changes without interrupting the machine cycles. To retrieve the results, we use WinSCP. This is a secure file transfer protocol client that allows us to access the PLC's internal memory. We pull the generated output.log file out of the PLC runtime environment and transfer it over to the IT side for review. This is the resulting output log text file. The contents display sequential rows, each featuring a precise timestamp next to our steadily incrementing activation integer. This structured, time-stamped integer dataset is exactly what predictive maintenance algorithms require to accurately track machine wear and tear over time. This rich data generation happened entirely on the edge hardware, without adding a single millisecond of latency to the actual machine control. While this is a simple motor start example, the same architecture can be applied to increasingly complex analytical requirements across the factory floor. By mapping C++ ports directly to IEC standard languages, modern PLCs transition from rigid operational controllers into dual-purpose, data-rich edge computing devices.